Okay, yes, welcome to our class for real data, continuous data sampling distributions. And our topic for discussion today is uniform distribution. So perhaps before going into details, maybe we try to find out or discuss what does uniform distribution mean. With the uniform distribution, we refer to a form of a probability in which each possible outcome of your interest has equal chance of occurring. That is the probability or the likelihood of an event to occur is the term throughout your sum of interest or your population of interest. In other words, the probability of occurrence of an event is equal throughout. So if the probability for it is 0.5, it will be 0.5 throughout. Enter whichever observation you pick from your population. If the probability is 0.6, then it will be 0.6 throughout the total sample or the population of your interest. Now, such events which have equal chance of happening, has equal likelihood of happening, it forms a form of a distribution which is known as a uniform distribution. We have some examples here. Number 1 and 2 is for discrete case, and I'll not speak about that. But number 3 and 4 is for continuous uniform distribution, which is our discussion for today. So, for instance, example number 3 speaks of the random number generators. Think, for instance, you are generating numbers from, let's say, numbers between 1 to 10, random numbers. Okay, so any number in between 1 to 10 has equal likelihood of happening. That I need 5 numbers between 1 and 10. So it can be 1.5, can be 2, can be 3.5, can be whichever number which is in between 1 and 5 can come up. Or if you ask someone to guess the time, you just ask your friend, what's the time? Can you guess? So if you ask 5, 3, or 2 persons, each one will guess the time which he or she thinks that is correct. But whoever guesses the time, or everyone who guesses, the guessing will follow uniform distribution in the context that whichever time one will tell you, the likelihood or the probability will be the same. So such events or such outcomes in which the likelihood of happening is the same, they fall or they form a probability distribution which is known as a uniform distribution. This is just some clarification on the uniform distribution, that sometimes it's also referred to be a rectangular distribution. Okay, meaning that you have 2 points, okay, or limits, the lower limit and the upper limit, and the probability is somewhere uniform, it does not change. So in the x-axis being the limits, that's from point A to point B, and in the y-axis you have the probability, which is uniform, does not change. So in such situations, the uniform distribution is also referred to be a rectangular distribution. And you can see here is the definition, okay, that a random number x is said to have a continuous uniform distribution over intervals theta 1 and theta 2. So you can use whichever letters you wish. I've used theta 1, theta 2. Someone else can use maybe A to B. Okay, whichever letters you wish to use, which you are comfortable with. Okay, now a random number defined over the intervals of theta 1, theta 2, okay, is said to follow a uniform distribution if its probability density function is given by that formula, that is f of x equal to k, if that value is defined between theta 1 and theta 2, otherwise it will be equal to 0. Okay, so theta 1 and sorry, I think yeah, they're typing errors, but it means theta 1 and theta 2 is just repetition, and the two parameters of a uniform distribution. That is the lower limit, but also we have the upper limit, which is theta 2. These are the two important parameters which we'll be trying to deal with in regarding uniform distribution. Now, as usual, as we know in probability, we have what we call a probability density function. Now, if our function is defined between 2 points, which are theta 1 and theta 2, so what we expect means if we integrating that function from within the given limit, it should equal 1. That if f of x is a function defined over theta 1 and theta 2, those are the upper limit and the lower limit. If you integrate your function with respect to x from theta 1 and theta 2, now that particular function should equal 1. Now remember, what the value of f of x from this slide? From the previous slide we saw f of x equal to k from that side. So we can substitute k in our integral function right here, that f of x equal to k. So instead of f of x we replace with the k. So we'll be having integral from theta 1 to theta 2 k dx. Okay. Upon substituting, integral of dx will be equal to x. Okay. If you substitute theta 1 and theta 2, then you have k, and you make k the subject. We have k equal to 1 over theta 1 minus theta 2. That is the integral. You integrate k dx from theta 1 to theta 2, and then you make k the subject. Okay. If you make k the subject, you are having k equal to 1 over theta 2 minus theta 1. So remember, from the previous slide we had f of x equal to k, 0, otherwise k theta 1 up to theta 2. So we have seen now k equal to 1 over theta 2 minus theta 1. So instead of k, we can substitute these values, theta 1 over theta 1 minus theta 2. So our function changes to be u, means uniform distribution, x is our variable, and theta 1 and theta 2 are the two parameters, equal to 1 over theta 1, theta 2 solve, and theta 1. For theta 1, let's equal to x, let's equal to x2, theta 2, and 0 otherwise. So this function here is the same as the function we saw in the previous slide, only that we have substituted 1 over theta 1, 1 over theta 2 minus theta 1 for k. Okay, so you may find some literatures using the function of this form, 1 over theta 2 minus theta 1. It can be different letters, but the same notation. Or the other literature, they use just a constant, a single constant, which is k. So if you find k, you have to bear in mind that k equal to 1 over theta 2 minus theta 1. Now this is the probability density function for our random variable which follows a uniform distribution. Okay. The thing to remember is the parameters, that we have two parameters which are theta 1, theta 2 and theta 1. Okay, and it should be defined within that particular interval. The other thing is that function, if it's not defined within the given limits, then the function will always be equal to 0. That's the point to note. So this is the triangular distribution, the concept we saw earlier, that a uniform distribution is sometimes referred to a rectangular shape. Sorry, not triangular distribution, rectangular distribution, meaning that it takes a shape of a rectangle. So as you can see from here, we have our limits theta 1 and theta 2. Okay, if you go back to the previous slide, it is these limits here that our function is defined between theta 1 and theta 2. Next, we have our value here, our probability, which is 1 over theta 2 minus theta 1. And you can see the horizontal line, is it yellow or which color is that one? Something like yellow. Okay. Now that is horizontal, meaning the probability is uniform or is constant throughout the given interval, which is theta 2 and theta 1. So the line parallel to x-axis shows that the probability for this particular function is uniform, does not change from the lower limit, which is theta 1, to the upper limit, which is theta 2. That's why this kind of a distribution is also referred to be a rectangular distribution or a uniform distribution, to mean that the probability is uniform throughout, it does not change. Now, if you refer back to the previous slide, we've been given two intervals from theta 1 up to theta 2. Now, what's happened if we refer or you think of the interval from negative infinity up to theta 1 and think of the interval from positive infinity from theta 2 to positive infinity. Okay, it means our function will be equal to 0 if and only if for all values of x, in other words, which are less than theta 1, it means from theta 1 to negative infinity. And our function will always equal 1 if we substitute any value which is beyond the upper limit, which is theta 2. Okay, meaning that the probability for that any variable which is uniform distributed does not exceed 1 and does not go beyond 0. So whichever value you substitute, whichever x value you substitute, which is beyond the lower limit, will always give you 0, and whichever value you use, which is above the upper limit, will always return the value of 1. So these are in other words, they are the two possible probabilities, that our probability will always be between 0 and 1. We never go beyond 1. That is the essence. Now here are some examples. I think we shall have time to work on the examples and see how to come up with the probabilities. That is the second session for this lecture. This example 3, we'll work on these examples to see how to come up with the solutions. Now, remember the concept of moments. Okay, we discussed some issues referring to moments in case of discrete distributions. So with regard to moments with the uniform distribution, this is the formula. Okay, and we have said a uniform distribution is rectangular in nature. It's called a rectangular distribution. So this is the formula for the rth moment of a rectangular distribution, which is defined between interval θ1 up to θ2. Okay, so if you remember, our function is the f of x. In the previous slide, we said f of x equal to k, or f of x equal to 1 over θ2 minus θ1. So in the first equation right here, that is mu dash r equal to θ1, θ2, x to the r f of x dx. Instead of f of x, we can substitute the value of this function, which is either k or which is 1 over θ2 minus θ1. So upon substitution, we have the value to the right hand side, which is 1 over θ2 minus θ1. This is the value of the function, integral from θ1 to θ2, x to the r dx. Okay, so you can integrate and simplify your function. You integrate it to x. Okay, and finally we have the rth moment for a uniform distribution of random variables, which is free from x. Okay, on the in bluish font, which is 1 over θ2 minus θ1, then θ2 power r1 plus 1, then minus θ1 r plus 1 over r plus 1. The text in blue font, okay, represent the rth moment of a random variable which follows a uniform distribution. So with this one, from this point, you can have the mean, you can calculate the variance, you can calculate the third moment, or whichever moment you can calculate by simply substituting the value of r. Now, for instance, let us see how to come up with the mean and how to come up with the variance. Okay. Now, mean, if you refer back to your concept of mathematics or statistics, the mean is the first moment, meaning that r equal to 1. So from the previous slide, we have seen the rth moment equal to 1 over θ2 minus θ1, then θ2 r plus 1 minus θ1 r plus 1 over r plus 1. This is the rth moment. So if mean equal to the first moment, means r equal to 1. So whenever there is r, we put 1. Okay, let's go and see. So wherever there is r, we substitute with the 1, because we are trying to find the first moment to get the mean. So our equation now changes to 1 over θ2 minus θ1, 1 plus 1. So you can see the first, we have substituted 1 for r. So it will be 1 plus 1 minus θ1, 1 plus 1. The second, the first, these ones, we have the first 1 plus 1. So the one which starts just after θ2 is for r. And the one which starts just after θ1 is also for the value of r. So 1 plus 1 makes 2. 1 plus 1 makes 2. So we have the equation to the right, which is a half, meaning 1 plus 1 from the denominator is a half. Then the numerator, it is θ2 squared minus θ1 2 squared, which is θ2 squared over θ2 minus θ1. So in the numerator, the difference of 2 squares, θ2 squared minus θ1 squared, the difference of 2 squares from the concept of, from the mathematics concepts. So upon simplification, this is simply writing θ1 minus θ2, θ1 plus θ2. You can see from right here. And this goes away, θ2 minus θ1 goes away. We have the mean then for any variable which follows a uniform distribution will be equal to a half θ1 plus θ2. What does it mean? It means if you have been given two parameters, the lower limit and the upper limit, and then you are asked to find out the mean of such particular variable. If it follows a uniform distribution, then the value for that particular, the mean for such particular distribution will be equal to a half θ2 plus θ1. In other words, a half lower upper limit plus the lower limit. That is the mean. Simple. If you think of the variance, variance is the second moment. Okay, variance is the second moment, and it's given by the formula, as you can see from the slide. So from the formula for the moment, which is bluish in color, in place of R, wherever there is R, we substitute 2 to mean that we are trying to find out the second moment. Okay, we are looking for the second moment. So if you substitute 2 for R and you simplify, you end up having 1/3 theta 2 squared plus theta 1 theta 2 minus theta 1 squared. I'm repeating that when you speak of a variance, means you are trying to find out the first place you have to find out the second moment, okay, because the one which is used in computation for the variance, we take this we take the difference with the second moment and the mean squared. Okay, so the first place you have to find the second moment, and this is obtained by just substituting 2 in the place of R. So instead of R, you just substitute 2. Okay, you will have theta 1 cube, theta 2 cube, so minus theta 2 cube divided by 3. And if you simplify this, and this is mathematics now, simplification, you end up having 1/3 theta 2 squared plus theta 2 plus theta 1 minus theta 1 squared. That is the variance, the second moment. So to get the formula for the variance, means we have to take the difference between the second moment and the first moment square. Okay, that we substitute the second moment from the first moment from the second moment, we have our variance. Now mu2, sorry, this should be variance, not mu2. Mu2 is the mean. Okay, now variance will be equal to the second moment minus first moment, and if you simplify the equation, you'll be having mu2 equal to 1/12 and 2 plus theta 1 squared. So this is the formula for the variance. You just take the square of the two parameters, you divide by 12. We shall work on this to see how to come up with these things. So, ladies and gentlemen, this was a brief video on uniform distribution. In the next session, we shall be trying to see how to calculate, to make things into practice, to have some questions for practice, to find the uniform distribution, the probabilities, to calculate the means, and to calculate the variances. Thank you for listening, and we meet in the next session.